right? sp2 hybridization. This will be number 2. sp2 hybridization. What exactly is sp2 hybridization? As the name implies, in this type of hybridization, one s orbital intermixes with 2 of the p orbitals. Not all the 3 p orbitals are involved in the hybridization. Okay, so the type of hybridization in which one s orbital intermixes with two of the p orbitals Now tell me, if two of the p orbitals are involved along with one s orbital, how many hybrid orbitals will be produced?
3.
3. With two of the p orbitals, so as to produce a total of 3 sp2 hybrid orbitals is called sp2 hybridization. Okay, so total of 3 hybrid orbitals are produced. And how do we show it? With the help of the orbitals. Say this is s orbital. This is s orbital. These are the two p orbitals that are involved in hybridization. And let me show the unhybridized p orbital that did not take part in hybridization as this green color. Okay. The green one is not involved in hybridization. As a result, what will happen? This is going to give us 3 sp2 hybrid orbitals. With 33.3% s character and 66.7% p character. Because total of 3 orbitals are involved. Out of the 3, one of them is s. So 1/3 obviously stands for 33.3%, and 2/3 are p orbitals. So that is 66.7%. Now, don't forget the green colored p orbital that did not take part in hybridization. So that remains as pure p orbital. Okay. This did not take part in hybridization, so it will remain as it was. Rest two p orbitals along the z axis and the x axis have taken part in bond formation. I mean, in hybridization. Now, these 3 sp2 hybrid orbitals that are produced, they try to rearrange themselves so as to have minimum repulsion and maximum stability. And last class, we discussed that when it was sp3 and 4 hybrid orbitals were produced, The shape acquired was tetrahedral. But now the shape acquired will be no longer tetrahedral because 3 hybrid orbitals are produced. So they are going to rearrange themselves in this manner, making a bond angle of 120 degrees. And what about the unhybridized p orbital? That will be lying perpendicular to the molecular plane. So the green one that I have shown is present here. So this one is referred to as the unhybridized p orbital. Unhybridized p orbital. So hence we can say that in sp2 hybridization, 3 hybrid orbitals are produced. One of the p orbital remains unhybridized. And when these 3 hybrid orbitals are produced, so they are going to arrange themselves so as to form a trigonal shape. 3 of them will lie on the same plane, whereas the unhybridized p orbital will remain perpendicular to the plane containing the hybrid orbitals. I hope it is understood.
Yes, sir. Yes, sir.
So further, you can write down after drawing this diagram. The 3 sp2 hybrid orbitals arrange themselves trigonally, making a bond angle of 120 degree, whereas the unhybridized p orbital lies perpendicular to the plane containing hybrid orbitals. The 3 sp2 hybrid orbitals arrange themselves trigonally, making a bond angle of 120 degree, whereas the unhybridized p orbital lies perpendicular to the plane containing the 3 hybrid orbitals. Done? Can I proceed?
Yes, sir.
Okay. All of you have written?
Yes, sir.
Fine. So the next thing that we are going to discuss is the examples under sp2 hybridization. What are the examples under sp2 hybridization? Under the examples, we can write, to start away with, boron trifluoride, okay, BF3, ethene, CH2 double bond CH2, sulfur dioxide, SnCl2, and Men. And out of all these examples, we will study in details about the first two, boron trifluoride and ethene. So boron trifluoride, of course, is a monocentric molecule with boron as the center, whereas ethene is a dicentric molecule, just as ethane was. So we first talk about the shape of boron trifluoride. Boron trifluoride. So boron being the central atom, we are going to discuss about its energy diagram. 1s, 2s, 2p. So 1s2, 2s2, 2p1. This is the ground state. So as you can see that in the ground state, there is only one unpaired electron, but the valency of boron in BF3 is 3, which means that the ground state electronic configuration does not match up with that of the valency shown by boron, and hence we need to take the help of excited state. So in excited state, one of the electrons from 2s is going to make jump to the 2p, and thus there are 3 unpaired electrons, and thereafter there will be hybridized state. So what's happening in hybridized state? This is sp2, and in sp2 this s is going to intermix with only 2 of the p orbitals, producing a total of 3 sp2 hybrid orbitals. But the fourth one, which remains unhybridized, will be drawn in this manner. Again, I am repeating, the 2s orbital intermixes with 2 of the 2p orbitals, producing a total of 3 sp2 hybrid orbitals. Whereas the third p orbital, which did not take part in hybridization, remains as such. So all the electrons whosoever were present in the hybridization, in the orbitals taking part in hybridization, will be now equally distributed among the 3 sp2 hybrid orbitals, which means that all the 3 sp2 hybrid orbitals have got 1 unpaired electron each. And we have just now discussed that anyone who shows sp2 hybridization will acquire a trigonal shape with a bond angle of 120 degree, and it has an unhybridized p orbital. And in case of boron, the energy diagram says that the three hybrid orbitals have got one unpaired electron each, and the unhybridized is vacant. It is not taking part in hybridization. So since it is vacant, we are simply going to shade it off as it is of no use. So our boron is prepared, and now according to the formula BF3, it is going to invite the three fluorine atoms. And let us see that in case of fluorine atoms, whose atomic number is 9, 1s2, 2s2, 2px2, 2py2, 2pz1, the unpaired electron of fluorine lies in the 2pz, and therefore fluorine is going to come to form bond with the boron with the help of its p orbitals. And we know that p orbitals are dumbbell shaped, and from the three different directions the fluorine atoms will come. So all the three which have been marked by red are fluorine. They are pure p orbitals of fluorine. Remember, fluorine does not undergo hybridization because it is always the central atom that undergoes hybridization. So boron is undergoing hybridization. So after it forms bond with the fluorine, you get 3 sigma bonds. Can anyone help me out? What is the nature of this sigma bond? Can anyone tell me that what is the nature of the sigma bond formed between boron and fluorine?
Head on head, sir.
No, I'm not asking that. What I'm asking is, what is the nature of the sigma bond? This lobe is sp2, isn't it? Is not it sp2?
Yes, sir.
And what is this? Fluorine? Is it not p?
P.
So what will be the type of sigma bond? Will it not be
P2P.
sp2p sigma bond, isn't it?
Yes, sir.
Similarly, what about the other two? They are also equally sp2p sigma bonds, isn't it?
Yes, sir.
So all the three are sp2p sigma bonds, suggesting that all of the three have equal bond lengths. Is it clear? Is the shape of BF3 clear to you? Frankly, tell me. Anyone having any doubt? Please clear it out. It's important that you must understand it. Yes? Any doubt? Is it clear? Tell me.
Yes, sir.
So why have I shaded off this unhybridized p orbital?
Sir, because it is of no use to us right now.
It is? Can you repeat? It is what? Tell me.
Sir, because it is of no use to us.
It is of no use. Why is it? Why it is of no use to us? It does not contain any unpaired electron in it, isn't it?
Yes, sir.
Okay. Have you completed? Can I proceed further?
So please wait.
Okay, no problem.
Sir,
Yes.
sir, this time it is MCQ pattern, so how will it come?
It may be asked in various ways, the type of sigma bond present in boron trifluoride, isn't it?
Yes, sir.
So if the basics are clear, then you can go for any type of question asked.
Okay, sir.
Suppose it might be asked that what is the type of hybridization of boron in BF3? Okay.
Yes, sir.
But how many, the total number of sigma bonds in boron trifluoride is of how many types? So there are possibilities of various types of questions being asked. Can I proceed further?
Yes, sir.
Okay. Now let us try to do the next one. That is shape of CH2 double bond CH2, ethene. Who is the central atom?
Carbon.
Carbon. So what is the electronic configuration of carbon in the ground state? 1s2, 2s2, 2p2, isn't it? And in the excited state, one of the electrons jumps, and that is 1s2, 2s1, 2p3. And because the hybridization is still sp2, so this is going to intermix with these two as usual to form the three circles, and one of the p orbitals remain unhybridized. So but the difference between boron and carbon is, in boron, this
Sir,
unhybridized,
Sir,
yes,
can I explain that one again? That one is to ground state data once more.
1s2, 2s2, 2p2 is the ground state electronic configuration of carbon. Carbon has atomic number of 6 or not?
Yes, sir.
So one more electron I have added up, that's it. With respect to boron, it has one more electron, na?
Yes, sir.
So boron had atomic number of 5, carbon has atomic number of 6. So I have added an extra electron. That is what I have done. Clear?
Yes, sir.
Okay. Now you see the whole pattern will remain same if it is sp2 hybridized, and thus we can say that only the difference lies in the number of unpaired electrons. Okay, so the number of unpaired electrons will be 4 now. In boron it was 3. So here in the unhybridized p orbital you have an unpaired electron. Are you able to see it? But previously when it was boron, it was vacant or not? Are you getting the difference? Yes, tell me, are you getting the difference between boron and carbon? What difference do you get between energy diagram of boron and energy diagram of carbon? Where is the difference you are getting? Anyone answer me?
Sir, the unhybridized
The
orbital has
unhybridized p orbital was vacant in case of boron, but in case of carbon, even the unhybridized p orbital is also half filled, isn't it? Adrika?
Sir,
Tell me.
sir, can you please explain once more that in carbon having 4 valency, why is it sp2?
Because if you look at the formula, last class, didn't I tell you how to find out sp2 hybridization, sp3 hybridization, and sp hybridization? If the carbon atoms are doubly bonded, the type of hybridization shown by carbon is sp2 or not?
Yes, sir.
Remember?
Yes, sir.
Understood?
Yes, sir.
Okay. Because carbon can show any three type of hybridization, sp2, sp3, or sp. So by looking at the original molecule, we can make out that whether carbon will show sp3, sp2, or sp, because both the carbon are doubly bonded. And last class we discussed that doubly bonded carbon are sp2 hybridized, isn't it? That is why we have drawn the diagram for sp2 hybridization. Clear?
Okay, sir.
How many such carbons are there who are showing sp2 hybridization? In ethene,
So 2.
2. Have you drawn the energy diagram for carbon, everyone?
Yes, sir.
Yes, sir.
Okay. So remember that there are 2 such carbons who are sp2 hybridized. So let us try to draw the diagram. Any part which is not clear, immediately ask. Can I put 1 unpaired electron on all the hybrid orbitals as well as the unhybridized p orbital or not?
Yes, sir.
In the same way, there is another carbon who is also showing the same kind of see whether it is understood or not. Is it clear? This is for one carbon which is sp2 hybridized. This is for another carbon which is also sp2 hybridized. Clear or not?
Yes, sir.
Yes, sir.
Okay. Now tell me, those sp2 hybrid orbitals which are facing outwards will overlap with what according to the formula?
Hydrogen.
Hydrogen. And what is the shape of hydrogen? Dumbbell or spherical?
Spherical.
Spherical. So they are going to overlap with hydrogen. So how many carbon hydrogen sigma bonds are formed?
4.
4.
4. And what is the nature of these 4 sigma bonds?
sp2s.
Very good. sp2s. So all these 4 are sp2s sigma bonds. Now there is one more sigma bond which is formed between the 2 carbon atoms. What is the nature of this sigma bond? Yes,
sp2 sp2.
very good. sp2 sp2. Now finally look at the pure p orbitals that did not take part in hybridization. They are parallel to each other, and we have learned in previous class, when 2 p orbitals, both of which have unpaired electron in them, are parallel to each other, what type of bond they are capable of forming? By overlapping above and below? Pi bond, isn't it? Understood?
Yes, sir.
Okay. So hence when I write C double bond C, one of them is sigma. And what is the nature of this sigma? sp2 sp2. and the other is pi, and pi is always formed between two pure p orbitals that are parallel to each other. And as far as the bonding between the carbon and 4 hydrogen atoms are concerned, all of them are sp2s sigma bonds. Understood?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so draw it. This is the shape of ethene molecule. You must be aware that it is an alkene, and doubly bonded carbon are always sp2 hybridized. Okay.
Yes, sir.
Okay. So this was sp2 hybridization, and we have discussed two structures in details according to our syllabus. Then we move on to sp hybridization. sp hybridization. So how many p orbitals are involved in sp hybridization? Tell me.
One.
Only one. The type of hybridization in which one s orbital intermixes with one of the p orbitals so as to produce a total of two sp hybrid orbitals is called sp hybridization. Is called sp hybridization. So that p orbital which takes part in hybridization, let me show it with the help of the black, and the rest two which do not take part in hybridization, let me show it with the help of green. So total of two hybrid orbitals will be produced. With 50% S and 50% P character. Whereas the two p orbitals that did not take part in hybridization are mutually perpendicular to each other. Now, if there are two hybrid orbitals produced, which shape is most comfortable shape for the two hybrid orbitals, in which they will have minimum repulsion and maximum stability?
Linear.
Very good, linear. So say this is the internuclear axis. Okay, so they are going to form 180-degree angle. And the other two unhybridized p orbitals will be lying mutually perpendicular to each other, as well as to the axis containing the two hybrid orbitals. So whosoever shows sp hybridization will acquire this type of shape. The green ones are unhybridized or pure p orbitals. They may or may not contain electron in them, and that will be clear when we go to the individual examples. If they contain unpaired electron in them, they will be responsible in pi bond formation. And if they do not contain any unpaired electron in them, so they will be of no use. Can I rub the upper part?
Yes, sir.
The two sp hybrid orbitals arrange themselves linearly, making bond angle of 180-degree. Whereas the unhybridized p orbitals lie perpendicular to each other, as well as to the axis containing the hybrid orbitals. So this is what we have written, whatever we have drawn here. So a total of 3 axes exist, and in sp hybridization, one of the axes will be taken by the hybrid orbitals, and the rest 2 will be taken by the unhybridized p orbital. So these are 3 axes which are mutually perpendicular to each other. So let us say that if this is the z-axis, then this will be the, say, x-axis, and this will be the y-axis. So since hybridization occurs only in one axis, So we can say it to be linear hybridization as well. If 2-axis that we got in sp2, it was a planar hybridization. And if all the 3 axes that we discussed last class under sp3, it was tetrahedral hybridization. So example that we are going to discuss under this are beryllium fluoride and ethine. As we can see, the triple bonded carbon are sp hybridized, and beryllium also is sp hybridized because this is inorganic molecule, and I have already given you a formula how to calculate the hybridization for inorganic molecule. And for organic also, I told you that if triple bonded carbon you come across, it will be sp hybridized, isn't it?
Yes, sir.
Okay. So at first we are going to discuss about beryllium fluoride. So who is the central atom of beryllium fluoride who is undergoing sp hybridization? Tell me.
Beryllium.
Beryllium. Shape of BeF2. So because beryllium is the central atom, we are going to discuss the energy diagram for beryllium, whose ground state electronic configuration is 1s2, 2s2, 2p0, because its atomic number is 4. But of course, the ground state configuration does not tell us anything about its bonding capacity, because there is no unpaired electron. But according to the formula, beryllium shows valency of 2. So therefore, we need to take the help of excited state, where one of the electrons will be excited to 2p from 2s. And in hybridized state, this S is going to intermix with any one of the p's, preferably the one with unpaired electron, and therefore a total of 2 hybrid orbitals will be produced, which we call as sp hybrid orbitals. And 2 of them did not take part in hybridization, so they remain as it is. And the electrons present in these 2 pure orbitals will be equally distributed. See, is it understood or not? Is it clear?
Yes,
Sir,
sir.
could you please explain this?
Okay. Now, we know that beryllium fluoride is sp hybridized. How to find out whether it is sp hybridized or not? Tell me. Add up the valence electrons. Remember the formula that I gave you?
Yes, sir.
And if it is less than 8, divided by 2. If it is greater than 8, divided by 8. So that way, beryllium fluoride will give us sp hybridization. Now, what is sp? S will intermix with only one of the p's, isn't it?
Yes, sir.
How many hybrid orbitals will be produced?
So 2 hybrid orbitals.
And how many unhybridized p orbital will remain?
So 2.
So this is what I have drawn. Understood?
Yes, sir.
Okay. So just now discussed that if anyone is sp hybridized, it is going to show this type of formation. And the unhybridized p orbital in case of beryllium will be of no use. So we can shade it off. Why it is of no use? In case of beryllium, why these two unhybridized p orbital are of no use? Yes, anyone who can help me out? Why we have shaded off these two unhybridized p orbital of beryllium?
Because they have no paired electrons.
They have no
Unpaired
electrons
un-
at all.
Yes.
They have no electrons at all. And these two have unpaired electrons or not? Yes. This is this, and this one is that, isn't it?
Yes, sir.
Okay, now what they are going to do if they contain unpaired electron in them, whom they are going to invite?
Fluorine.
Fluorine. And for fluorine, what orbital I am supposed to show?
Dumbbells.
Dumbbell.
Orbital.
So this is one fluorine. This is another fluorine. So they are going to form two sigma bonds. What is the nature of the sigma bond?
SPP.
See whether it is clear or not. Is it understood?
Yes, sir.
Yes, sir.
Yes, sir.
Can I
Yes.
move forward? Can I go to the next example of CH triple bond CH?
Yes, sir.
Is it a monocentric or dicentric molecule?
Dicentric.
What is the hybridization of each carbon?
SP.
Okay, so let us draw the energy diagram for carbon. Carbon has atomic number of 6, 1, 2, 3, 4, 5 and 6. Excited state and hybridized state. Understood? It is only the electrons that are different. Rest, the basic format remains the same, whosoever undergoes sp hybridization, isn't it? Done?
Yes, sir.
Okay. How many such carbons are there in ethyne?
2.
2. As it is dicentric, so for each carbon we have this type of diagram. Now even the unhybridized p orbital associated with each carbon will have unpaired electron, isn't it? Yes or no? So if carbon undergoes sp hybridization, there will be two hybrid orbitals and two unhybridized p orbitals, all of which contain 1 unpaired electron each. And same way, the other carbon will also have the same kind of configuration. So what will these two do, which are facing outwards? With whom they are going to form bond? Tell me.
Hydrogen.
Hydrogen. So at the two corners, we are supposed to draw two spherical shapes. Now, what will these two p orbitals do, which are parallel to each other?
Pi bond.
Cycles.
How many pi bonds are possible?
4.
2. Pi 1, pi 2. So let us see what are the total number of bonds formed. All these bonds are formed on the internuclear axis. This is SPS. This is also SPS or SSP. What is this type of sigma bond formed between the two carbon atoms?
SPSP.
SPSP. So total of 3 sigma bonds and 2 pi bonds are formed in ethyne molecule. Understood? Is it clear or confusion is there? Anyone having any confusion, please clear it out.
Sir, how many sigma bonds?
Tell me, how many sigma bonds do you see on the internuclear axis?
So 3.
3. 2 of them are carbon hydrogen sigma bonds. One of them is carbon carbon sigma bond. What is the nature of carbon hydrogen sigma bond?
Or SSP.
SSP by SPS. Both are same things. And what is the nature of carbon carbon sigma bond?
Or SPSP.
SPS. Clear?
Yes, sir.
Okay. See, pi bond formation is only possible when minimum there are 2 centers in a molecule. Pi bond is not possible with monocentric molecule because you must have 2 p orbitals which did not take part in hybridization, and they must contain unpaired electrons in them. Then only the p orbital is formed, otherwise not. I mean, pi orbitals are formed, but pi bond is formed. Done? So here I would like to mention one thing, that some of you might get confused by looking at the number of pi bonds. Though there are 4 lines, but each pi bond is represented by 2 lines, one above and one below. So it's not 4 pi bonds that are formed. There are 2 pi bonds only that are formed. Okay, can I proceed?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So after discussion of sp3, sp2 and sp, we now move on to hybridization involving d orbitals. So d will also be involved, and we have seen that hybridization may be sp3d, sp3d2 or sp3d3 as well. The fourth type of hybridization that we discuss is sp3d hybridization. So as the name implies, here one s, all the three p and one of the d orbitals will be involved in hybridization. The type of hybridization in which one s, all the three p and one of the d orbitals So there are 5 d orbitals, but not all d orbitals are involved. One of them will be involved to form a total of 5 sp3d hybrid orbitals is called sp3d hybridization. Okay, so total of 5 hybrid orbitals will be produced, because according to the rule of hybridization, the number of hybrid orbitals produced is equal to the number of pure orbitals involved in hybridization. So rather than drawing the diagram, I'm writing 1s, 3p and 1d will be producing 5 sp3d hybridized orbitals. So you can calculate the percentage s character, p character and d character also. Total of 5 orbitals are involved, out of which only one is s. So 1/5 will be 20%. One is d. So d is also 20%. And rest 3 will be p. So this will be 60%. These 5 sp3d hybrid orbitals arrange themselves to acquire trigonal bipyramidal shape. Okay, so we have discussed already in VSEPR theory that if there are 5 bond pairs, the best acquired shape is trigonal bipyramidal. So here also, as 5 hybrid orbitals are produced, so the best acquired shape will be trigonal bipyramidal, and 3 of them will be lying on the same plane, making a bond angle of 120 degree, and the rest 2 which are perpendicular will be forming 90 degree. So these 5 hybrid orbitals that will be formed will be aligning themselves along these 5 lines to get this particular shape. So examples are many. PCl5, then ClF3, XCF2, etc.
Sir, could you explain this structure again?
Which one? The
Sir,
shape?
this structure.
Okay. The shape is trigonal bipyramidal. Did you attend the class on VSEPR theory?
Yes, sir.
So we have discussed that when 5 bonded pairs were formed, so how did they arrange themselves? 3 of them were lying on the same plane, making a bond angle of 120 degree. And the rest 2
Yes.
are perpendicular to the plane, making bond angle of 90 degree, isn't it?
Yes, sir.
So here total of how many hybrid orbitals are produced? 5 or not?
Yes, sir.
So how are they going to arrange themselves so as to have minimum repulsion and maximum stability? 3 of them will be lying on the same plane and they will be called equatorial hybrid orbitals, and 2 of them will be arranging axially. That means they are perpendicular to the plane. Clear?
Sir, all the hybrid orbitals are of the same shape.
Are on the?
Sir, are all of them of the same shape?
Yeah, that's one of the important criteria of hybridization, that the hybrid orbitals which are produced are of equal shape, size and energy. All of them are equal in size.
Okay, sir.
Done? Can I proceed? Can I go to the example of PCl5?
Yes, sir.
Okay. So PCl5 is required under sp3 dehybridization. For that, we need to discuss the central atom of PCl5, which is phosphorus, having atomic number of 15. And from the formula that I gave you last class, you can make out that phosphorus will be sp3 dehybridized. So let us try to understand shape of PCl5, where P is the central atom. So phosphorus, if you look at the electronic configuration, it is 1s2, 2s2, 2p6, 3s2, 3px1, 3py1, 3pz1. So just consider only the valence shells in the energy diagram, because as such, the first shell and second shell are not involved in hybridization. So we are going to draw starting from 3s, 3p and 3d. So ground state electronic configuration of phosphorus is 3s2, 3p, 3. So 3d in the ground state is vacant. But because the valency of phosphorus is 5, but the electronic configuration in the ground state shows that it has only 3 unpaired electrons. So we need to take the help of excited state, where one of the electron from 3s will make a jump to 3d, making a total of 5 unpaired electrons. Then only the pentavalency of carbon can be explained, of phosphorus can be explained, sorry. Because before going to hybridization, the valency must be properly explained. So now we have 5 unpaired electrons, so we can explain the pentavalency of phosphorus. So this s, these 3p and one of the d orbitals will intermix producing a total of 5 sp3d hybrid orbitals, whereas the 4 of them will not take part in hybridization. So they are sp3d hybrid orbitals. And all will get the share of 1 unpaired electron each. And these are unhybridized d orbital that did not take part in bond formation. So this is the hybridized state of phosphorus. Yes, can I proceed? Done?
Yes, sir.
Okay. So remember, we have 5 sp3d hybrid orbitals of phosphorus, all of which contain 1 unpaired electron each. And we have already discussed that these 5 hybrid orbitals are going to arrange themselves in trigonal bipyramidal shape. So along these 5 lines, you put in the hybrid orbitals, all of which have equal shapes. And all of them have 1 unpaired electron each, as it is for phosphorus we are discussing. And just now we have discussed in energy diagram that phosphorus has 5 unpaired electron. Now, once the phosphorus is prepared, it is going to invite the chlorine atom. And when you look at the electronic configuration of chlorine, just like fluorine, the chlorine also has unpaired electron in p orbital. And therefore, from all the 5 different directions, the chlorine will be coming to form a total of 5 sigma bonds. Can anyone name the type of sigma bonds that are formed here? The 5 phosphorus chlorine bonds that are formed will be of what type of sigma bond?
sp3dp.
sp3d
p.
p. All of them are same. So this is the shape of phosphorus pentachloride. So 3 which are lying on the same plane making bond angle of 120 degree are equatorial bonds, and 2 of them which are lying perpendicular to the plane are axial bonds. But according to the concept of hybridization, all 5 bonds are exactly of equal bond length because they are sp3d p sigma bonds. So all these which I have drawn as red represent chlorine atoms. And it is always the central atom that undergoes hybridization, not the side atoms. Side atoms have a last door entry after the central atom prepares itself after hybridization.
Sir, here unhybridized orbitals are not required.
Unhybridized, not required because they do not contain any unpaired electron in them. So they will not be involved in any bond formation.
Okay, sir.
Done? Can I proceed?
Yes, sir.
Okay. Move on to the fifth type, sp3d2 hybridization. Now, more or less, you get an idea that as we keep on increasing the orbitals, the number of hybrid orbitals will also increase. Total of how many hybrid orbitals will be produced here? In sp3d2, tell me. Yes, anyone? How many hybrid orbitals will be produced now? 6. And if there are 6 hybrid orbitals, which do you think is the best acquired geometry so as to have minimum repulsion and maximum stability?
Octahedral.
Octahedral. Very good. The type of hybridization in which 1s all the 3p and 2 of the d orbitals intermix so as to produce a total of 6 sp3d2 hybrid orbitals is called sp3d2 hybridization. So here also, to avoid complexity out of shapes, we are simply writing 1s 3p and 2 of the d orbitals will produce 6 sp3d2 hybrid orbitals. And as you said that these 6 hybrid orbitals will arrange themselves so as to have minimum repulsion and maximum stability. And the best acquired shape is square bipyramidal, which is also called octahedral. So along these 6 lines, you need to put the hybrid orbitals. All are equal. And when we get into the particular examples, then only we can put in the electrons. The most common example is sulfur hexafluoride, xenon tetrafluoride, bromine pentafluoride, etc. And we will be discussing about SF6 in particular. Tell me after you have finished drawing so that we can get into SF6 structure.
Done, sir.
Okay. So under sp3d2, we discuss shape of SF6. So central atom is sulfur. So let us draw the energy diagram for sulfur by drawing only the valence shell 3s, 3p, 3d. So sulfur has atomic number of 16 with configuration of 3s to 3p4, 3d0. This is the ground state. How many unpaired electrons do you find in the ground state of sulfur? Yes,
2, sir.
only 2. But according to this formula, sulfur should have how many unpaired electrons before combining with fluorine? Yes.
V.
The formula is SF6. So how many unpaired electrons sulfur should possess before combining with fluorine? 6. So if you excite one of the electrons, then you are going to get only 4 unpaired electrons, which is not sufficient enough. And therefore, there will be double excitation. 1 electron from this and 1 electron from this. Okay, so there will be double excitation. And therefore, in the excited state, you can have 6 unpaired electrons only when 2 electrons are making jumps. Now you can explain the hexavalency of sulfur. So far we were having excited state in which only 1 electron was jumping. But here, if you make jump of only 1 electron, sulfur will show tetravalency. But according to the example given, sulfur must show hexavalency. So for that, 2 of the electrons must jump. And then in the hybridized state, these 3 and these 2 are going to intermix to produce a total of 6 sp3d2 hybrid orbitals. And these 3 will not take part in hybridization, will remain vacant and is of no use in bond formation. And all are going to get the share of 1 unpaired electron each. This is the hybridized state. हो गया?
Yes, sir.
Yes, sir.
And finally, as there are 6 hybrid orbitals produced, so they are going to arrange themselves octahedrally with 1 unpaired electron each. And because there are 6 unpaired electrons, so there will be 6 fluorine atoms with their dumbbell shapes, which will be invited to produce 6 sigma bonds. This is for sulfur, all of which contain 1 unpaired electron each. and fluorine from 6 different directions will be coming. So what is the nature of the sigma bonds that are produced finally in SF6? Yes.
sp3d2s.
sp3d2
P.
it's not S, it's sp3d2p, because fluorine will be utilizing its p orbital. Only hydrogen utilizes the s orbital. So all the 6 sigma bonds that are produced are sp3d2 p sigma bonds. I hope this much is clear to all of you. These red orbitals symbolizes which atom?
Fluorine.
Fluorine. And the central one with black? Yes, which atom is symbolized by these 6 black
Sulfur.
hybrid orbitals? Sulfur. Sulfur is the central one. Okay. I hope it is clear.
Yes.
Yes, sir.
So suddenly, if you are given a molecule and you have to find out what hybridization it will be showing, so use that formula. Suppose sulfur hexafluoride, 6 plus 6 into 7 will be 48 electrons. So 48 is to be divided by what?
8.
So 8 6 are 48. So 6 stands for what? sp3d2 or not? Isn't it?
Yes, sir.
So this is how we can calculate directly what hybridization will be shown by the central atom. Okay, so this much is required for your hybridization part. So next day we'll take another important topic of chemical bonding. Thank you. Good night, all of you.
Thank you,
Thank you,
sir.
sir.
Thank you, sir. Good night.